It's my pleasure to announce the last conference of the afternoon, and in principle the last talk of the afternoon, the last talk of the conference. But I remind you all that tomorrow there are also many interesting talks this day for the general public. We've talked by some of the particularly interesting people, so try to come tomorrow. So this is not yet the end, but it's officially the last talk. So I introduce, I'll read it from here. It's Davide Gaiotto, who will speak on geometric. No, it's changed. Then I better read this, what's written here.
Oh, sorry.
But what's written here is geometric Langlands applications of boundary conditions for maximally supersymmetric Langlands.
Okay. So indeed, I would like to discuss which sort of consequences in geometric Langlands one can derive from statements about concerning generic boundary conditions for n equal 4 superior Mills. So let me just remind you of the physics setup. So you can take n equal 4 supersymmetric Yang-Mills theory and do a twisted compactification on a Riemann surface C. So if you just reduce the theory on C, you get something that has 4,4 supersymmetry in 2 dimensions, in the remaining 2 dimensions. And you can think about it as a sort of a gauge linear sigma model, where the target of the gauge linear sigma model is the cotangent bundle of the space of connections on C. And the gauge group is just a space of gauge transformations on C. So the supersymmetric vacua of this system are the solutions to the Hitchin equations on C, modulo gauge transformations. So these are literally the F term and D term constraints for this 4,4 gauge linear sigma model. So you solve Hitchin equations, you get a vacuum of this theory. The space of vacua is the Hitchin moduli space. Now, for many purposes, you can just think about this as being a sigma model with this target space. This is sometimes slightly imprecise, and especially when at loci where this moduli space is singular, and then the gauge degrees of freedoms might become important. Or mathematically, some kind of Stucky geometry of this quotient. But today, I will do my best to stay away from those places and to just make statements which are sigma model statements. So the way I want to modify the setup is to include the boundary conditions in n equal 4 superior Mills. This is one of the ways you can produce a boundary condition for the 2-dimensional sigma model. You don't do anything funny to the space-time, you just put a boundary in the 4-dimensional space-time. It's not the only way you can get boundary conditions. There are many other ways with other possible applications, but this is what I'm interested in today. And even more specifically, in order to when I put a boundary condition at the origin of R+, I'm picking a half BPS boundary condition with a full 3-dimensional n equal 4 supersymmetry and superpoincaré symmetry. Again, this is a constraint that can be relaxed for some applications, but it's a useful. This is a sort of a setup. It's a set of things, of objects, which we understand pretty well. So it's a good thing to look at. Now, when you compactify this system on a Riemann surface, there is an extra choice to do due to the fact that this boundary condition breaks half the supersymmetry. So there are sort of 2 ways you can adapt the original twist to this setup. I call them the BAA twist and the BBB twist, simply because this boundary condition will descend to either a BAA brane or a BBB brane in the sigma model, in the Hitchin moduli space. Now, thankfully, somebody yesterday discussed what a BBB brane and a BBA branes are. I will review it, but at least the terminology is something you've encountered before. So a BAA twist concretely will essentially be a complex Lagrangian brane in the moduli space of Higgs bundles. While the BBB twist will give us hyperholomorphic B brane. I'll try to explain what that could mean. Again, on the Hitchin moduli space. So as you see, the either Lagrangian manifold or the brane will depend on the choice of original boundary condition in 4 dimensions. Now, S-duality in Nicole for supermills is supposed to be the physical motivation for geometric Langlands duality. So the first obvious question you can ask is, what happens if I act with S-duality on some system which has a boundary? So on general grounds, the boundary condition for the gauge theory with gauge group G will map to a new boundary condition for the gauge theory with gauge group G dual. So there are pairs of boundary conditions which are related by S-duality. The specific, there is an algorithm which in principle allows you to figure out which boundary condition is S-dual to another boundary condition. This was worked out by Ed Witten and myself a few years ago. Sometimes you can start with a very simple boundary condition and end up with a very complicated dual boundary condition. But in some situations, and string theory provides a lot of examples, you can start from an easy boundary condition and end up with another easy boundary condition. So applying our operation to these two branes, we're going to get geometric Langlands dual objects. More precisely, I can do a BAA twist or a BBB twist of this boundary condition. I can do a BAA twist or a BBB twist of this boundary condition. S-duality sort of exchanges the two twists. So the Lagrangian associated to one brane, to one boundary condition, will be mapped to the BBB brane for the other boundary condition, and vice versa. So each S-dual pair of boundary conditions upstairs in the gauge theory gives us two possible candidate mirror pairs in two dimensions, two possible geometric Langlands dual objects. Now, BAA branes and BBB branes are not exactly what mathematicians working on geometric Langlands are talking about, of course. But so this is the Kapustin and Witten interpretation of geometric Langland, which relates BAA branes to D modules on the space of G bundles on C. And it relates BBB branes to sheaves on the space of local systems or complexified local systems on C, representations of the fundamental group. Okay, so this is a statement. If you have a pair of mirror two-dimensional branes, you compute the D module or the sheaf, you're supposed to find geometric Langlands dual things. So, and there are also another idea is that a lot of important objects and operations that you can do in the mathematical setup have a four-dimensional origin. So in Kapustin and Witten in particular focused on the action of line defects on boundary conditions for dimensional and superior mills, which descended to statements about Hecke transformations. Okay. So in order to get to our final answer, there will be a few steps. First, we need to learn how to descend to two dimensions, and then we need to convert the two-dimensional statement into D modules or sheaves. Now, how does the boundary condition in for supermills look like? The typical example is the following. You take your gauge theory, you have it survive at the boundary, you let the gauge group survive at the boundary, and you couple it to some three-dimensional degrees of freedom, some general conformal field theory, not even conformal, some general quantum field theory in 3 dimensions with G global symmetry. So the space of boundary conditions for an equal supermills is at least as big as the space of quantum field theories with symmetry group G. It's a pretty big space. Now, and in principle, the Champaton bundles for these branes, the BBA and BBB branes, are essentially spaces of ground states for this 3D theory compactified on C. If you know what those words mean, these are pretty closely related to Rosansky-Witten twist, or mirror Rosansky-Witten twist, or the 3-dimensional quantum field theory. Now, in order to do calculations, ideally, we would need to have some reasonable description of this quantum field theory. If you give me some abstract quantum field theory, with, of course, clearly I cannot compute the ground states of that theory. If you give me a quantum field theory which has a Lagrangian description, there is a pretty good chance that I'll be able to compute the ground states. This is unfortunate, actually, because it excludes a lot of interesting examples. So I say it again, the techniques described today essentially require the quantum field theory to have a semi-classical description, to be the, something given by some matter fields and some three-dimensional gauge fields, perhaps. On the other hand, the sort of boundary condition which you would need to produce, say, Hecke eigensheaves, does not belong to this class. I have some ideas on how one could try to generalize these calculations to situations where the Lagrangian description is poor or absent, but they're very conjectural, and I'm not going to mention them further today. I believe there are some ways to use conformal blocks for some vertex operator algebras to build this data, to attach vertex operator algebras to 3D theories, which would compute the data you need. Okay, but even if we don't get Hecke eigensheaves, we're going to get a very large class of interesting dual pair objects, which might include things that interpolate between different gauge groups, perhaps. Now, let me see. So in the work with Edward, we just proposed a laundry list of ingredients you can use to build a boundary condition. There are a variety of things you can do. You can start with you can take the original gauge group, you can reduce it to the boundary, you can add something which you call a numpole. But luckily, even a very complicated boundary condition can be decomposed into simpler ingredients, especially if you have a Lagrangian description. Some of these ingredients actually have been discussed before, and I'm not going to discuss them further today. I really want to focus on this particular setup where the gauge group is essentially unbroken, and I'm putting some matter fields at the boundary. But in general, if you want to think about boundary condition, there is sort of this picture you can have in mind that some complicated boundary condition can be resolved into a sequence of maybe simpler interfaces followed by a boundary condition. So in principle, as long as you understand enough of these simple interfaces and you know how to project them down to 2 dimensions, you can compute the 2-dimensional image and then compose the 2-dimensional images, which is something that I believe is known how to do. There are operations like taking convolutions of sheaves, which can be done once you have the 2-dimensional data. And this is fortunate also because, as I was saying, string theory gives us a lot of examples of very simple interfaces which can be combined to make very general theories. Okay, so the most important class of examples for me today is the following. I take the sort of boundary conditions that the gauge group survives, and I couple it to hypermultiplets. So hypermultiplets are sort of the matter fields in 3-dimensional and for quantum field theories. Each hypermultiplet consists of 4 scalar fields and a bunch of fermions, which transform in some representation of the gauge group. More specifically, hypermultiplets transform in symplectic representations of the complexified gauge group or quaternionic representations of the gauge group. So the basic piece of data that I need to start doing calculations is just a symplectic representation of your complexified group. Now remember that the space of, okay, there's something I should say. So, right, I want to describe the BAA twist of this system. So I want to describe it as a complex Lagrangian submanifold in Hichy moduli space, more precisely in the complex structure where these are Higgs bundles. So there are other ways to produce boundary conditions which give you Lagrangian submanifolds in other complex structures, but boundary conditions, Lorentz invariant boundary conditions that I'm studying in this talk, always give you BAA branes, so complex Lagrangians in the space of Higgs bundles. So a Higgs bundle, remember, is a pair of a bundle and an adjoint Higgs field, which is holomorphic, modulo gauge transformations. Now, in order to define my Lagrangian submanifold, I'm going to consider some auxiliary space. This auxiliary space consists of a bundle together with a choice of a holomorphic section of these so ME is the bundle associated to the principal G bundle by the representation M. Okay, so the fibers are just copies of M, which transform with transition functions built out of E. And then I tensor it with the square root of the canonical bundle. So the reason to do that is that the BAA twist makes the hypermultiplet scalars into spinors. So these are the hypermultiplet scalars, and I'm asking for them to be holomorphic spinors on this Riemann surface. Now, there is a map from this manifold into the space of Higgs bundles. This is a symplectic representation, and so it has a moment map. Moment map is a quadratic expression whose target is the Lie algebra of the group. So I can write the equation phi equal moment map of Z. So this maps this manifold into the Higgs bundles. And I claim that this image is a complex Lagrangian. It's not obvious, of course, but intuitively, you can think about it this way. So roughly, the condition to have a lot of sections of this bundle is a constraint on E, so the more you constrain E, the more degrees of freedom in phi you get. But if you want to know why is this a Lagrangian manifold, well, of course you can just compute. You can just take the symplectic form and restrict it to this space. There is a perspective which I find useful, which is the following. Suppose you have the cotangent bundle of some manifold. And I give you a function of the base and of some extra auxiliary variables, C. I can look at these two equations. I can set the momenta, the coordinates on the fiber, to be the gradient of the function. And at the same time, extremize the function with respect to the auxiliary variables. This always gives you a Lagrangian submanifold. It's very easy to see. You can really take dx dp, then this becomes dx d of this, and then you can rewrite in terms of the derivatives of this. If you apply this general construction to this specific function, which is the integral on C of this sort of fermionic sort of first-order action for Z, you get exactly these equations. See, the variation of W with respect to the auxiliary parameter Z tells you that Z is holomorphic. The variation with respect to the connection gives you the moment map. Remember, phi is like the momentum conjugate to the connection. So this is a quick demonstration that this is going to be a Lagrangian submanifold. Well, otherwise you're going to get some term that looks like dx dc. And this is cancelled by. Okay, so these are general class of Lagrangian manifolds. There are a few variations on this construction, which is worth mentioning. For example, you could get a Lagrangian correspondence between a Lagrangian manifold in the product of two Higgs moduli spaces by doing something like this. You set the bundles to be equal and the difference of the Higgs fields to be this moment map. This is something that will happen across an interface where you have some matter fields, but the gauge group just goes through. Or you can try to add extra three-dimensional gauge fields. This makes the story more complicated, but gives you a much larger class of boundary conditions. So now you need hypermultiplets matter fields which transform in a representation both of the four-dimensional gauge group and of this auxiliary three-dimensional gauge group. You can sort of look at the same equation relating. So now you're going to have a section which is a section of the product of a G bundle and a G prime bundle. And I'm going to constrain, so this gives you more freedom because now I can pick a generic E prime bundle, but I'm going to constrain it more by setting to 0 the moment map of G prime. And then again, I look at the image in the space of Higgs bundles, and this is again a Lagrangian submanifold. Okay, so these are our BAA branes. Now, strictly speaking, I should give you a Lagrangian and a flat bundle on it. This map might have a non-trivial fiber above a point. And I believe you should take something like the cohomology of that fiber in order to get a flat bundle on the Lagrangian manifold. But I'm not 100% sure of which kind of cohomology. I think the standard de Rham cohomology, but I have some questions. So this gives you more generally a BAA brane. And actually, after Maxime's talk this morning, I wonder more generally how to extract from this some sort of extra data at the self-intersections of this Lagrangian manifold. Okay, so this is the BAA brane side. On the other hand, if you do a BBB twist of a set of hypermultiplets, you're supposed to get what's called a BBB brane. What is a BBB brane? So a BBB brane, well, I don't know what a BBB brane is, to be fully honest. I mean, I don't know it physically, but I don't know precisely the mathematical data that you attach to it. I know examples of BBB branes. I know that, for example, if I take a vector bundle with a connection which is of type 1-1, whose curvature is of type 1-1 in all complex structure, that would be a BBB brane. So you can see it as a B brane in every different complex structure just by taking the holomorphic bundle in the complex structure. There is presumably some notion of hyperholomorphic shift too. The simplest example is I take an hyperkähler submanifold of my manifold and I put another holomorphic bundle on that. But there is probably more general things. Instantons are examples of hyperholomorphic bundles. Okay, but in general, from physical grounds, a thing that should give me an hyperholomorphic sheaf is a sheaf of ground states of some quantum mechanics with 4 supercharges. So if you have a quantum mechanics with some moduli space which is hyperkähler, the ground states of the quantum mechanics should give you an hyperholomorphic sheaf. This is also the TT, you can think about this sort of TT star philosophy. And mathematically, this is related to the notion of non-transform. So non-transforms are a very general way to get hyperholomorphic sheaves. You build some moduli, some Dirac operator parameterized by your moduli space, and you look at the zero modes of the Dirac operator. And again, if you do it properly, this will be an hyperholomorphic sheaf. And we'll see an example in a moment. So indeed, the basic ingredient I need to define my BBB branes is something called the Dirac-Higgs bundle. It was introduced by Hitchin, I believe, a few years ago. It has been studied by some of his students. So this is the co-kernel of a Dirac operator defined on C. So you take the solution of Hitchin equations, you package the connection in the Higgs field into a Dirac operator, and you look at the co-kernel and the zero modes. In each complex structure, you can compute this co-kernel by a cohomology. For example, in complex structure I, it's the cohomology of del bar plus phi wedge, acting on forms valued in the representation M. This is also called something called hypercohomology. It's typically also, I think, is pretty much the same as sheaf cohomology of this complex of sheaves. In generic complex structure, instead, it's just the Ram cohomology of forms valued in M. If you want to do geometric Langlands, this is what you want, because you want to think about it as a sheaf on the space of local systems, which is the Hitchin system in generic complex structure. Now, this is not the BB brane itself, but it's something we will use to produce the BB brane. So here I've been helped a lot by Kevin Costello. So essentially, you should think about this space of zero modes of the Dirac operator, active conforms, as a classical phase space which you need to quantize. In other words, this sheaf actually has an antisymmetric pairing, just integral over C of the wedge product of the forms contracted with the symplectic pairing of the representation. And you should quantize this space using this symplectic form. Concretely, so you want to build the Fox, you want to essentially build the Fox space, a Clifford module with the Clifford generators living in here. The simplest situation is where the hypermultiplet representation can be split into a complex representation and its conjugate. You might remember in the talk of Nakajima, he was taking the same constraint on the hypermultiplet representations because it does simplify a lot of calculations. So in that case, at least when this cohomology is concentrated in degree 1, the hyperholomorphic sheaf we want is just built out of the exterior algebra of this Dirac-Higgs bundle. So you take the Dirac-Higgs bundle for n, take the exterior algebra, normalize it by the square root of the determinant so that it's more symmetric. And that's the sheaf, the BBB brane we are going to attach to the boundary condition. If you want to add gauge field, three-dimensional gauge fields, the story becomes a bit more complicated, but perhaps not too much. So now you're taking, again, a representation of G times G prime, which gives you a sheaf on the product of the modular space of Higgs bundles or each insistence for G and G prime. And you want to do an untransform on the G prime factor. That means that you're going to build the Dirac operator out to that holomorphic connection we just built, look at the zero modes of that, and use them as a sheaf on the original Hitchin modular space, on the G Hitchin modular space. Again, it should be possible to, in each complex structure, it should be possible to reduce this to a cohomology calculation, some kind of sheaf cohomology calculation on the modular space of G prime Higgs bundles. So it should be doable. I'm not saying I know how to do it, but I'm sure there are a lot of members of the audience which can do this sort of calculations. OK, I'm sorry, this has been quite abstract. I'm going to give you a concrete example right away. So this is the simplest example of a boundary condition which has a nice S-duality behavior and is still non-trivial. So I'm going to consider a U1 gauge theory in 4 dimensions. U1 gauge theory in 4 dimensions with normal boundary conditions coupled to a single hypermultiplet of charge 1, which means that the representation M is just C plus C with weights 1 and minus 1 under the action of U1. This boundary condition has a beautiful property. It's invariant under S-duality. This is a very supersymmetric version of particle-vortex duality. In particular, that means that if you compute the BA twist and you compute the BBB twist, they're going to be mirror to each other. So let's do some calculations. I have a line bundle E. I tensor with k to the 1/2. I look for a section. I take the inverse of the line bundle, tensor with k to the 1/2, and look for a section. These are the two pieces in Z. The moment map is just xy. So I impose the constraint phi equal to xy. So let's try to understand this geometry. I can start by fixing the bundle first and looking for Higgs fields. Well, let's work in degree 0 at first. If this bundle has degree 0 and is generic, there are no non-trivial sections of this. Only x equal to 0 and y equal to 0. And so I get phi equal to 0. The first component of the Lagrangian if I think about my Hitchin modular space as T star of band G, I have the space of line bundles, and generically, I set at phi equal to 0. But on codimension 1 loci, a locus called the theta divisor, sections appear. One-dimensional space of sections for this and this simultaneously because of an index theorem. So now I have the possibility of non-zero x, non-zero y, one-dimensional line of possible solutions. I multiply them, and I get a one-dimensional line of phi's. So this component of the Lagrangian is the conormal bundle to the theta divisor. Now, the theta divisor will self-intersect in intricate ways, generating locations where the number of zero modes will of sections will go up, and the dimension of possible phi's will go up. And I don't know much about the geometry of the theta divisor, but I'm sure that there is a lot of fun statements to be had. So this is going to be the union of roughly true Lagrangians with these self-intersecting in complicated ways. Now, there is another perspective that we can use instead, which is the Hitchin fibration. Someone could. Not sure I can. Okay. So now I have a base of the Hitchin fibration, which is just parameterized by phi. I fix phi, and I'm asking what bundles are compatible with that. Well, suppose that phi has simple zeros. It's one form with simple zeros, has 2g minus 2 of them. Now you can pick some of the zeros, put them in x, some of the zeros, put them in y. That fixes the divide, that fixes E. So essentially, if you call xi is the zeros of x and yi is the zeros of y, the bundle is the element of the Jacobian or shifted Jacobian with these coordinates, with this divisor, associated to this divisor. In general, I can do this splitting any way I want. So in degree D, I'm going to get 2g minus 2 choose d plus g minus 1 possible bundles. So I get a multi-section of my Hitchin fibration, which has those many points above a generic fiber. So this picture is useful to get a geometric intuition about mirror symmetry. Because remember that mirror symmetry is just fiber-wise T-duality, which means if I apply T-duality on the fibers, mirror symmetry should give me a sheaf with this rank. Now, there are some subtleties in mirror symmetry and geometric Langlands duality for abelian theories. So there are on one hand, there is a choice of degree. There are many components of the Hitchin moduli space. On the other hand, there is some unbroken U1 gauge symmetry, which means that really you should give me not just a boundary condition for the Hitchin sigma model, but also for the 2D gauge, unbroken gauge theory. So there is another number that enters there, some charge Q. And when you do mirror symmetry, you sort of exchange degree and Q. Concretely, I don't want to go into details in that because I don't understand it very well. But concretely, that means that you should add up all the sheaves over all the Ds. You expect to find in the mirror a sheaf of degree 2 of rank 2 to the 2g minus 2, which is just the sum of all of these numbers. Let's compute it. So now I need to do hypercohomology or sheaf cohomology of this complex. I take the line bundle, I go to line bundle tensor K by acting with phi. Now again, this calculation is particularly simple if the zeros of the Higgs field are simple and the bundle has degree 0, then I can get the answer from some paper by Hitchin and his students. And then you see that this bundle of zero modes of the Dirac operator becomes the direct sum of line bundles. Just the cokernel of this map at the zeros of phi. This is actually a more general statement. It works in any rank, but now I'm applying it to U1. Now I need to build a Fock space out of this, and that's what you get. A product over all the zeros of phi of a two-dimensional space for each zero. So you see it has dimension 2 to the power of 2g minus 2, as we were hoping to find. And moreover, if you stare long enough at these versus these, I'm sure you can convince yourself that each individual line bundle in this sum of these products of sums is just the mirror of that. So essentially, the xi's are the zi's for which you pick the first the second term, and the yi's the ones for which you pick the first. Okay. So at least in generic fibers, things work. Our S-dual pair, S-self-dual boundary condition descended to mirror dual BBB brain and BAA brain. Of course, there is the fiber at phi equal to 0 where things are very messy and complicated, and even just the fibers where phi has multiple zeros. I don't pretend to understand the full geometry well, but it's at least plausible that this could be mirror dual. Now, to do geometric Langlands, I should really give you a D module. I already gave you a sheaf because, as I said, you can just do the RAM cohomology of forms valued in M and take the Fock space of that if you want to do a sheaf on local systems. But for the BAA twist, I should just give you a D module. Now, it turns out that there is a general quantization strategy for all the Lagrangian manifolds of this form. The strategy is just to look at the module associated to contour integrals of e to the w over h bar, the C. You can convince yourself pretty easily that if you start taking derivative of an expression like this by x, you're going to pull down the derivative of w over h bar, right? So you can see that this gives a quantization of that relation. Okay, more general, right? So you can build a D module. You can also put holomorphic polynomials in C inside the integral. So you can build a D module of differential equations satisfied by this kind of integrals. Okay? Now, I want to apply it to this function. So what do I get? I get a path integral over the space of sections of this k to the 1/2 times m of this action. Yeah, here there should be an integral over C. I'm sorry. It dropped out. So these are something called symplectic bosons. This is a very well-known conformal field theory in 2 dimensions. So you can think about partition function beta conformal blocks for that conformal field theory, or you can just do the integral. You get 1 over the Pfaffian of the del bar operator. So this is a rank 1 D module, twisted D module, and this is my conjectural answer for what's the BAA brain for pure hypermultiples at the boundary. I'm less certain about what happens when I put gauge fields. Intuitively, we should just add a path integral over the 3 dimensions of the gauge fields for the G prime gauge group. I'm confused by some possible anomalies. Also, in principle, it should be possible to do things also mathematically, just working with convolution of convoluting this D module with a trivial D module for G prime. I don't know how to do the calculation. I have some conjectures based on conformal blocks for a coset current algebra, just taking the symplectic bosons and taking the coset by the 3-dimensional gauge group. But I'm not certain. A lot of things are working all right, but I've not worked through enough examples to convince myself that it's really correct. How much? I have lots of time. That's true. It might have been a bit too fast. I think I'll give more examples to the Blackboard, perhaps. Oh, excellent, excellent. Well, so first, let me give you some conclusions and future directions, and then maybe I'll walk through some more examples. So the first conclusion is that the BBAA twist and BBB twist of Lagrangian boundary conditions are computable. I mean, the original motivation of my work with with Witten on boundary condition was to produce things that could be used for geometric Langlands. But at the time, we did not know how to convert that physical knowledge into some mathematical statements. Now we have the dictionary to translate a lot of our statements into something mathematically precise. So as dual pairs of boundary conditions seem to give interesting examples of geometric Langlands dual pairs. Of course, as it has been probably manifest in the presentation, there are a lot of places where the calculations had to be tightened up and done better mathematically. I think it's a typo. But anyway, there are a lot of calculations to do, and most of those calculations are beyond my ability, so I hope to get help from members of the audience at some point. There are several ways to extend this. As I mentioned, there are some ways to do calculation with vertex operator algebras, and it seems to extend even to theories which are not quite well described by Lagrangian. So it seems to be plausible that you can, particularly using some results by Rastelli and Beam and other collaborators, to guess or work out some vertex operator algebras associated to general three-dimensional quantum field theories, or to a lot of three-dimensional quantum field theories, whose conformal blocks would give you the D-modules or sheaves that are required for geometric Langlands. But this has not been developed very much. I think I have some conjecture, reasonable conjecture for the vertex operator algebra, which should give you again sheaves, for example. But I have no idea how to compute the conformal blocks of that vertex operator algebra. So, something that should be worked in more detail is the action of line defects on these boundary conditions. So one can figure out how Hecke correspondences act on the corresponding D-modules. And finally, it should be possible to add ramification. So I've been doing some calculations with the student about that should allow to add surface defects to the four-dimensional gauge theory, and then ramification to the Hitchin system. The main tricky part is that these surface defects are going to end at the boundary. So now you need to give a boundary condition for the surface defect, which is something which is interesting. You need to couple really the boundary gauge theory, the boundary theory to the degrees of freedom on the defect. And there seem to be multiple choices. I don't quite know which one is the most natural. But again, it's rather computable. And actually, to be honest, a lot of the initial calculations were done in this setup because Riemann surfaces are somewhat hard for me, while complex plane with a nice irregular singularity at infinity is something I can deal with more easily. So this is definitely an interesting place to do calculations. Okay, so perhaps I can just list a few other pairs of boundary conditions or interfaces which occur in string theory. So the general way you can get boundary conditions or interfaces from string theory is to consider the tree branes, a bunch of parallel tree branes, which engineer n equals 4 superior mills. And then you can cross these D3 branes with other objects. For example, you could use an NS5 brane, or you could use a D5 brane. Here I put the same number of D3s on both sides, which means I get an interface between a UN and a UN gauge theory, or another interface between UN and UN gauge theory, but the numbers can vary across the interface. So this is a perfectly plausible situation, for example, where I change the rank of my gauge group while going across the interface. And the field theory meaning of these interfaces is very clear. They can be described very precisely. And S-duality interchanges them. So if you have an interface made out of D5 branes, it will map to an interface made out of an NS5 brane. So it gives you a lot of S-dual pairs. And then more generally, you can start stacking up sequences of NS5 branes and D5 branes, And to get S-duality, you just replace D5s with an S5s and an S5s with D5s. And finally, there is a very important tool which is called the Hanani-Witten move, which can be used to manipulate these configurations. I should have probably dotted this so that we distinguish an S5 from D5s. So a configuration like this, for example, can be deformed continuously into a configuration like this. Okay. But you create extra branes in the process. So there is a very specific rule that allows you to manipulate these configurations and relate different interfaces and do calculations. For example, the abelian example that I mentioned followed from a manipulation of this sort. When you start from something like this, you deform it to something like this, and then you apply S-duality to go back to this. Anyway, to just say that there is some graphical calculus that one can use to produce S-duality as dual pairs of boundary conditions and interfaces, which should be pretty useful. This can be generalized to other classical groups, and although things become a little bit trickier. So, for example, this boundary condition with a single D5 correspond to coupling and hypermultiplet in the fundamental representation of UN. So you have UN gauge theory, it goes through, and it couples to something in the fundamental representation. So, for example, the BAA twist would be some Lagrangian of this sort. But these X and Y are fundamentals of SUN. And the BBB twist will be something like, will be something built out of the Dirac-Higgs bundle in the fundamental representation. The Fock space built out of this. This is S-dual to an S5 boundary condition. An S5 boundary condition, instead, you really have a boundary condition. It's not, so here the gauge group was going through. Here you get boundary conditions for the gauge group on the two sides, and you get some sort of bifundamental hypermultiplets here. So if you do the BAA twist, you get something like phi equal to xy, phi prime equal to yx. Okay, and BBBD twist will be some sheaf built, Dirac-Higgs bundle built out of bifundamental representation. Okay, so this is one nice example of S-dual pairs, which presumably is mathematically interesting. Another thing you can do is just to remove one of the branes. Then you get a nice interface between UN and UN-1, where the UN gauge group is reduced to UN-1. And on this side, you still get bifundamentals. I guess this might be useful to produce interfaces, functors, which change the rank of the Hitchin system, and so on and so forth. I'm done.
I thought this is an example of the Heisenberg principle, that the deeper the talk is, the shorter it can be. The product is a constant. So I hope there are people who can ask questions. I would be totally unable to, but who would like this thing? Maxime.
In fact, we talked with Davide during the lunch a lot about this stuff accidentally. It's not a question, just a remark. I think this hyperholomorphic sheaves were described by Verbitsky in his thesis 20 years ago. He has this whole theory of hyperholomorphic shifts, coherent shifts. Yeah.
Oh, excellent, excellent.
So
Thank
should
you.
Exist.
I was missing the reference.
But it's not an archive, it's before archive. Yeah.
Okay, that's why I was missing the reference.
I was a little confused by your S-duality in U1. Did you say that Neumann boundary conditions actually are S-dual to, again, something that's Neumann type?
Neumann plus 1 hypermultiplet is S-dual to Neumann plus 1 hypermultiplet.
But how would you say it in D5, NS5?
So here I have the U1 gauge group ending on an S5, which means that there is a Neumann boundary condition. The D5 produces an extra hypermultiplet. It's really literally D3 strings stretched between the two. And it's via Hanani-Witten, and its duality maps back to itself. If I just had Neumann without hypermultiplets, then it would map to Dirichlet boundary conditions.
Thanks.
Could we go back to the Dirac-Higgs
Yes.
bundles? So you wrote d bar plus phi wedge now, and then you jumped to cohomology, sheaf cohomology.
Yes.
I would have thought that the physics would more naturally lead to L2 cohomology for that operator.
I mean, it's on the Riemann surface, so now when we discuss it on the Hitchin moduli space, then definitely.
Wait, I missed something. Oh, I see. This is on the Riemann surface. No,
That's right. So
you're not looking at d bar cohomology on the Hitchin moduli space.
Not until you introduce a three-dimensional gauge group. Then you would definitely have to look at the bar cohomology.
But then you're going to need to, okay, good. So then you're going to need to do d bar cohomology on the...
Presumably L2 normalizable.
And then it should be L2 normalizable.
Yes.
Okay, so the real question is, if you do that, then have you thought about consequences of no exotics if you think of this as a limit of a mass-deformed n equals 2 theory? Right, so think of, you could perturb to an n equals 2 theory with a mass n equals 2 preserving mass deformation. Then you have no exotics theorems. And then you could take a limit back.
Yeah, but on the Hitchin moduli space itself, how do I... The no exotic was something about monopole moduli space, right?
Yeah, well, that's why I'm asking the question.
I'm
so
not
I'm
sure
wondering if there's an analog of that story.
Yeah, I'm not sure how to connect to the Hitchin moduli space. Although in some cases, Hitchin moduli space is periodic monopoles. But
any more hands? Then I suggest we thank the speaker again and remember about tomorrow morning, beautiful lecture starting at 9:30.
One last chance to thank the organizers who did a great job.